topic is geometry shaders and how those work. And geometry shaders are, they're programmable stage. I'm going to pull the rendering pipeline up here with yet another overview of the rendering pipeline, since there's another of these things. And so this is the one at chronos.org, and it's probably the most relevant visualization of this thing for us anyway, especially seeing they've compacted down detail and steps we can't change anyway. You start with the vertex specification, and then we get to the vertex shaders, which we've been writing. And after you do all this stuff to take primitives and turn them into fragments, we have the fragment shaders. So there's a couple possible stages we can have after the vertex shader. We have the tessellation, which is they came later than vertex shader, the geometry shader, excuse me. And you get the geometry shaders, today's topic. Now, note that they're after the vertex shader, which is kind of important when you do things inside them. Okay, last time we copied trees, which was pretty good, and we made like a whole field of trees, if I remember right. And I went ahead and backed these up to a soft thread. So actually, if we wanted our example back, a soft thread, it's in here
somewhere.
Hey, there it is. So this should actually be where things were at the end of last time. We had our visualization flying through the trees, and then over the top we come, and yeah, pretty cool, except for that cursor sitting there, like a giant cockroach stuck to a projector screen.
I was gonna say it looks like a fly, but
it's bigger though. Like, if you look at that thing, I mean, I've never seen a fly quite that big. It's like a horsefly or something.
yeah, I was gonna say I've seen flies that big, but
If it's a fly that big, it probably bites.
usually.
Okay, so that was good. Now, we can actually do that with a geometry shader if we want to. And that's not necessarily the usual use case for a geometry shader, copying something from one place to another, but it illustrates how they work, and we can totally do it. So let's go ahead and do that, and we'll learn about geometry shaders and how they work while we do it. So they take input as primitives, actual primitives, and select comes after the vertex shader. But it's not in vertices. We get actual primitives, a complete line or triangle or whatever. Now, we don't necessarily get the same primitives as were drawn, oddly enough. So there's, let's take triangle strip for example. If you look at a triangle strip, here's a good triangle strip from OpenGL. So you give it these vertices, A, B, C, D, E, and F, and it draws these 4 triangles right here. So if we did that, we would get 4 invocations of the geometry shader. So the geometry shader would be run once per triangle, even though there's some of the triangles share vertices. The vertex shader would get run 6 times. So the geometry shader, in general, will be run less times than the vertex shader. Although you can turn that on its head if you want to by invoking it multiple times per primitive. But anyway, if you don't do that, then vertex shader 6 times, geometry shader 4, and it's pretty hard to contrive a geometry where you manage to run the geometry shader more times than the vertex shader. I was trying to think through if there's some kind of triangle fan, like completion at the end or line loop or something, and I could never quite get the geometry shader ahead in my head. Okay. Yeah. Yeah, you can do even with like a line loop, but not ahead. Okay, so anyway, that's what it takes as input, actual primitives. Okay, then output is also primitives. So the funny thing though is the primitives that come out, they'll eventually turn into fragments and get fragment shaded, but they won't actually get vertex shader. So you have to remember that when they're coming out. It also means that they won't, so that means that if you're using a transformation matrix and you're applying your transformation matrix in the vertex shader, the way we've been doing, and it won't actually get applied to the generated primitives. It has already been applied to the primitives that come into the geometry shader. But that means that your movements inside the geometry shader are relative to where everything ended up after transformation in the vertex shader.
That's it.
Yeah, it is.
So what's it for?
The geometry shader?
Yeah.
Adding stuff. Or you can subtract stuff from it too if you want to.
I see, so like you feed it in the basic primitive and then you add the detail.
Yeah, you can. That was one of the initial plans for these things. Now these came in OpenGL 3.2, and yeah, you can totally use it for geometry amplification. You know, you just take something and it's simple, and then you add more to it. We'll make a copy of the tree and do that in just a minute. But then in OpenGL 4, the tessellation shaders came in. And they actually come in two pieces. There's a tessellation control shader and a tessellation evaluation shader. And there's an intermediate fixed function piece that does the actual tessellation and makes a bunch of primitives for you. And so it's intended to implement level of detail based on distance and that kind of thing. And it does it more efficiently. But anyway, yeah, that was an original plan for the geometry shader. Another thing the geometry shader has been used for is doing computation. Since you can actually run its output into a buffer and then read it later, you could compute something using it. I do that later, but it's kind of superseded by the compute shader in that regard. Okay, so let's write one of these things. That will be fun. Okay, so in this bush demo from before, we had this tree, and I think we made a forest partway through, and we'll go ahead and take out our forest, which is kind of sad. I sort of like the forest. That was right here. And if we take out this forest here, I think we'll be left without any trees at all, not even one. Yeah, okay. Actually, we can just grab the cube demo, the current version of the cube demo. That sounds good. Okay. Now, the irritating thing about this one is it already has the geometry shader. Oh, push. Okay. Has to be remade. Yep, already got all three. That's okay. That'll save us a whole lot of time overwriting the thing anyway. I'm making typos. Okay, but I got to be careful to show you everything and not skip over it, as is my usual practice. Okay, so let's go ahead and drop out a bunch of this thing, and we'll put it back later. Okay, so I'm going to pull a few pieces of this in order to make it kind of a simple and easy demo. And so we'll pull all of that stuff, and that, and all this. Okay. I think that still probably works. There might be a conflict when we run it. Yep, it's got the F color. Remember this one from last time? We'll just use the rabbitator instead of the gerbolator. And that will be fine. The tree will be ready. There we go. Okay. So we got a super simple geometry shader on here. Okay. So what it does, it takes in lines. You can ignore the invocations thing right now. It's just invocating it once. And so we have input there, or lines, and then we got output. And this has a line strip. So the lines there, you have to set the way that the input is going to come into this thing. So you're going to take lines, triangles, points. You can use points. Points become kind of useful with these because you could put in, say, a point and then generate the rest of your geometry right here in the geometry shader. So if the point is an asteroid, you know, here you could build the rest of the asteroid right there. Anyway, So the types there, it's got a few different types. Let's grab the kind of reference here. Okay, so there's the chart I was looking for. If you have an open GL, like GL points, it's points. If you have a GL lines or GL line strip or GL line list, then it becomes a lines. And so the same kinds of things happen with the other ones. You can have lines adjacency or triangles adjacency. Let's see, for example, triangles describes triangles as GL triangles or triangle strip or triangle fan. And so if any of these things have been drawn, you get in triangles. And the output is kind of even simpler in a way. The outputs, you can have points, you can have lines strip, or you can have triangle strip. And they just function the same way as the the GL equivalents, except that you actually write those points or line strip or triangle strip. The odd thing is, these are kind of a constant and identify something like that. But yet when you use them inside GLSL, it's lowercase. So have to remember that. Kind of violates the convention. I should show my operating systems classes. They might appreciate that. Okay, so then for the output, we want to draw the tree here, and all we have is line strip. But we don't really have to reinterpret that, because if you take a line strip and put exactly 2 vertices in it, then you have a line. So no big deal there. So inside this main, we have this GL position. And GL position is kind of weird inside here. GL position is the name of the variable that holds the current position that we're working on. And whenever we say emit vertex, a vertex is generated at GL position. So that's what it does now. Remember, GL position was in the vertex shader too. If we look at the vertex shader for the bush, it's got this GL position, and we set GL position to the position of that particular vertex. So the big difference inside the geometry shader here is whenever you feel like you got GL position at a spot you want a vertex, you just say emit vertex, and out pops a vertex. And you can do that however many times you like. Then at the end, you say end primitive. Now, you have to say how many times you'd like that to happen up here, the maximum number of vertices that can be put out. I don't know what happens if you just leave this out. It looks like a Python thing here, right? Let's find out. Learn something new. Okay, we didn't say. Okay. Oh, the tree is gone. So you have to say what the max vertices are. It's actually only 2 on this one. So I guess it's okay if you overstate it. Just not understate it. Okay. We do that and say end primitive. If we wanted to put out a second line, we could just say end primitive again. Suppose we take this whole thing up here and duplicate it. And down on this second one, we change the position. So we can say, the original position here, and we can go ahead and add to it. Let's shift it over in the X direction a little bit. Now, since it's a vector, we can deconstruct it or something like that. That sounds like a hassle. If we instead say we want a new vec4, which is what it is, remember we can add 2 vec4s here at GLSL just like this. So we're going to say an X coordinate of 2, and then we'll zero all the others out. If we were to say 3 there, everything would be weird. Okay, let's go ahead and run this. Apparently we have not doubled it in a good way. Oh, here it is. We said max vertices is 2, and then we emitted 4. That's too many. So the later ones are just ignored. There we go. Now we've got 2 trees and a stack. So we can totally do that. Now, we can say end primitive twice. Let's go ahead and comment that one out. And this is going to make the trees look joined. Like joined a lot.
I like that one better, actually.
Like that one better?
It looks like one tree. That's nice and dense.
Keep the bottom to the branch.
So what's happening there, so our primitive is a line strip, right? So we get 4 vertices in a row. That means 3 lines. connecting each of the 4 vertices. So if we don't say end primitive right here, then we get a line section there. However, if we do end the primitive there, that ends our line strip, and then we start a new line strip. And so that way we don't end up connecting the lines from one to the next. Okay, suppose we wanted to do something else funny with the other tree. Let's say we want to take the other tree and we'll just reverse the x and y axes. Dot yxz. Done both of them. Okay. Oh, this is the vec3 yxz. We're adding it to a vec4, and GL position is a vec4. So we need our last one there. I think it's set as O in here. It might also be A. It's A. There we go. So
That's fun.
it looks distinctly weird with the x and y axes reversed. Okay. By the way,
Instead, transpose the y and the x and z or something.
X and Z would look a lot more normal since the tree would still be upright. Remember the word squizzle there? That would be a great thing to put on the test for like a multiple choice or something. What is squizzle? So we changed it so instead of X, Y, Z, O, well, X, Y, Z, A, it's giving us an error that O is invalid. So instead of X, Y, Z, A, we went Y, X, Z, O. So we took a couple of the vector components and switched them for everyone in it. It's called a squizzle.
That's weird.
Yeah, remember that, Alex? I wonder if he actually watches these.
Could you do say
Yes.
a negative x there?
Oh, like minus x? I don't think it'll like that. Man, that's a good idea. If you wanted to do that, say we want to just reverse one. So instead of squizzling, we'll leave that all alone. And we'll take this, but we'll multiply it by something. We'll say times vec4, and what's it going to do here, though? Maybe a cross or a dot product, or I'm not sure this is a good idea, actually. Let's find out what happens. -1. Oh, we can say 0 to multiply. Okay. We'll do the same thing down here. I don't know what happens. Very interesting.
Yeah,
Hey,
flips it
we're-
upside down.
Totally. It multiplied them component by component. That's what I was hoping it would do. But then I was thinking if it would do something different than that. Okay. So we can do stuff with the second one there. No problem. Okay. So that's great, and originally this is the only way that you could do that kind of thing in a geometry shader. It wasn't until OpenGL, some version later than 3.2, that they added this invocations thing up here, where we can say different invocations. So I'll go ahead and say invocations is 2. So now we've got 2 invocations to work with, and we also have to take in a variable to control that. And I had an original one, GL invocation ID. It's spelled like that. Nope, it's not. Underscore goes in the wrong spot. I noticed you need underscore wrong. Okay. So we've got an invocation ID, and we can say if GL invocation ID is 1, then we'll go ahead and do this first bit right there. Okay. And else, then we go and do the part down here. Okay. So now our max vertices that we're outputting is actually only 2, because regardless of which path we go, each of them has 2 vertices. And so I think this is going to do the same thing. Oh, we got something there. Syntax error. No semicolon. There we go. Exact same thing. Great. The reason for doing that is it gives you a little bit more parallelism. When we say that we're going to have 2 invocations, I was looking for this thing here. It was not there. When we got 2 invocations like this, we can run this on 2 separate units on the card. And so that's what we're trying to do is make a whole bunch of simple operations for this card to do with a lot of shaders at once. I almost said 1,920 again, but actually this computer here has only 1,600 and something, so it's got the 970. Okay, so that's invocations. Good, okay, so copying a tree, yeah, we did that. Layouts, we said with lines. Oh, I didn't mention this, but you probably picked up on it. GLN in there is an array of the vertices that came in with our primitive. So if we took a line, we got 2. If it's a triangle, then it's got 3. Okay, so the output, we went through that. Image vertex, good, yes, we do that. Oh, let's copy colors. That's a good plan. Okay, we didn't copy the colors over from the original tree. And so if we look at our original colors here, we've got this FCA, which is the, oh, that's not how it looked for us. I don't remember what we had. Oh well. So we got the fragment shader here that takes in this thing F color. Go ahead and re-enable that. Okay. So F color has got to be an invec form up here. And so that's got to be determined for the vertex. If we run it right now, it probably won't work. It says F color is not declared as an output from the previous stage. And you notice it clarifies here. Previous stage versus like the vertex shader. Because the vertex shader was not the previous shader, it was the geometry shader. So that's the one that's got to make this F color. Okay. G. Okay, so we can have one of those. We can have out vec for F color. Okay. Do we expect a 4? Yeah, we expect a, well, we didn't expect a 4 here. We expected a vec 3. That's okay. We can just expect a vec 4. That's fine. Okay, that can go away. We can just say F color. Okay, so we're expecting a vec 4 to come from the geometry shader. So all we have to do is make one. F color equals, and so we had a red before. We'll go ahead and make the green tree here. That's kind of a tree green. Okay, and then for the ones down here, let's say this is the blue tree. Oh, 6 is not okay. 0.6 is okay. Range is 0 to 1. Okay, look at the blue tree. We'll go for 0.6, and then we'll go for less green, like 0.2. It might be like the teal tree or something. I don't know my colors very well. Okay. So there you go. You can maybe.
Oh, it's blue.
Okay. Well, Matt can see it. I don't know if anybody else can. It's further away. Looks pretty good on the screen here.
Pretty good on the screen here too.
Yeah. If we really wanted to differentiate it, we could just like peg the red color on one of them.
I think we got a purple tree.
Yeah, we do. Okay. So we can pass them through with different colors. No real surprise there. The main thing to note here, when you do emit vertex, it'll also take your other out things. So we have this out F color here, and when we call emit vertex, it emits the vertex with this F color tagged. Then when we're in the fragment shader, it automatically has F color available, blended to for different amounts of that F color that are coming from the various vertices, being it's a primitive that you're dealing with a fragment from. So it really pretty much just works like the vertex shader there. Okay, so the actual vertex shader, cube.v.glsl. We have this out vec for FCA in here. And so we've got something called an FCA for each of these vertices. And you can see that we actually have this two-tone thing going on with FCA. So if we want to restore that, let's do it. Okay. So we'll take this tree over here and restore original colors using FCA. Okay. Now the thing about FCA though is we actually have 2 FCA values because we got 2 vertices. So it's now an array. Again, is it the vec 4 or vec 3? I don't remember. It's got to match. The vec 4. Okay, FCA. And this is going to be an array. So we can say FCA at position 0, and then for this other one, we want FCA at position 1. Okay. See what happens. Okay, so there's our original tree with a kind of, brownish wood kind of color until about halfway up, where it turns green. And then we've got our purple tree, still soldiering along next to it, because we left all that stuff alone in the geometry shader. Okay, so that's how you use in and out to pass stuff around into the geometry shader and back out of it, and that kind of thing. Okay, so the tutorial library, Sports GL Geometry Shader. I should show you how I put these things into the tutorial. Oh, and we'll lawnmower the tree at some point. Okay, that's better. Okay, so the tutorial. First thing is pretty easy, really. We put in these shaders up here. We had a vertex shader and a fragment shader. So the cube tutorial comes with these top two lines. So if you want to add a geometry shader, you just make an identical third line down here that's geometry shader. And the type of shader is a geometry shader. And you have to have a name for it. This really doesn't have to, you don't have to use this convention on the file names. There are two different conventions with GLSL file names. And there's nothing to stop you from making your own, of course. I haven't even set up my text editor to syntax highlight GLSL files correctly yet, although I really should. Or just tell it to do the same thing it does for C on them, that'd be pretty close. So anyway, we have a line like that. These variables, VS and FS, came from up here, so you got a GS. And then you just have to GL attach shader and attach your geometry shader program, or geometry shader to the program that contains the vertex and fragment shaders. And then it'll automatically get run. So that's really not too bad. Now, I think this tutorial, if you go to the common directory on it, it has a shader utils.cpp, and that's got a version here. The default version is like version 120 or something like that. So let's switch that back. Okay, so now it gives us an error in the vertex shader. Out can't be used with non-varying FCA. Anyway, so it's not going to quite understand these examples of the default version. Let's bring it up to like version 140. Okay, make cube. Okay, now we got a whole host of problems. Input, output, layer qualifier supported above GL version 140. Basically, it's again too old. You need to have version 150 or later. So, if we make this 150, I think our example here might actually work. Yeah, it works. So you need a version 150 or later. I've been leaving mine at 450, and that way it ensures the latest stuff. One reason to go later than that is we're actually going to be doing compute shaders at some point and tessellation shaders. Tessellation shaders require 4.0, which is version 400. Compute shaders, I think, are version 4.3, which is 430 in here. The numbering is very consistent now. So now it's like, well, why did I even bother to repeat that? Well, version 3.2 is 150. Okay. So that's version. So that has to be changed on the tutorials, and then it starts to work. Kind of another note on them. The modern tutorials that we've been using, modern OpenGL tutorials. That's actually not the ones we've been using. Maybe it was these ones. Maybe not. There's a lot of, actually this looks like the same site, just done differently. I think there's a link on the website. You could just go there. Okay. So the looking ahead on these tutorials bit, maybe they were referred to in a very first class. We'll start with that one, this one, the Wikibooks OpenGL programming. Okay. So I like their basic tutorials here, but then if you look for geometry shaders in here, there's only a GLES Craft 7.1 using it, And they use this kind of in a funny way, using GL geometry shader ext, and then they have to define a few other things for it and whatnot. So it comes out a little bit odd. I'm not sure that that's necessarily the best reference for these. I've been using this page at Kronos an awful lot. That's it's kind of the complete but a bit dry and not very tutorial-ish kind of reference. And it gives you kind of the complete standard there, and works really well. But then there's another one, there's a suggestion that you might want to look through for a geometry shader tutorial over here at Lighthouse 3D. And so they have a set of examples here and code that does stuff and whatnot. Not too bad. Okay, so that's some notes about reference. But of course, today's is a good starting point. Okay, let's learn more of the tree. With this tree, this shader here, okay, we'll learn more of this tree, the purple tree. So we have the option to omit 0 vertices if we want to. So over here, we could say something like if GLN at position 1, or position 0, doesn't matter, dot y, so y coordinate, is greater than 0, then return. So if we return at that point and stop running our shader without emitting any vertices, then we won't have any. So if we run that, the problem there, oh yeah, dot GL position, dot y. It is shorter. If we wanted to lawnmower both trees, we could just take that thing and put it right here. And I realize this indent is wrong, but now they're short. Or would we prefer to bisect the tree the other way? Ooh, maybe that was a bad choice.
Yeah.
So it depends on where it is. Remember that the geometry shader happens after the vertex shader. So we're dealing with the tree after it's already been moved to the right spot. So this rotating is already included in the coordinates that we're looking at. Now, in addition to that, the copy of the tree is the original tree shifted over a bit. And so what we're looking at is the original coordinates there when we're deciding whether to clip them off or not. Yes, the side lawnmower. So you could actually use this if you wanted to include some culling primitives that you just plain don't want to show. And if you cull them at this point, then they don't take any more time for rasterization or fragment shading or any of that kind of thing. And so it does take the video card, save the video card a fair amount of time. If in your geometry shader, you're just like, oh yeah, we don't even actually need this vertex. So you don't omit anything at all. Okay. And so if you were to just plain not emit anything, like ever, well, this is greater than -100, then we wouldn't emit anything at all from our vertex shaders. And if that's what's happening, then we just plain won't see anything.
Wouldn't that be emitting everything?
So if it's greater than 100, we return. So if we return at that level, then we don't do any of this stuff.
Okay, so we're emitting everything.
So we're emitting nothing. So this is like always true.
But nothing's being dropped.
That's right. Because we're not emitting anything. Oh,
So we're emitting
emit versus omit. We're not emitting anything.
Ah,
We're omitting everything.
oh, okay.
Sorry, yeah. Yeah.
That makes more sense.
Sure. Oh, here we go. I don't know if you're actually allowed to use define in here. But it would be kind of funny.
Yeah.
Okay, so that's vertex shaders and culling things. Yeah, it looks kind of odd the way it's done there. Since, yes, oh. Well, oh, since all of that. I thought I had that going. Okay, So anyway, culling, yes, good. Definitely can cull things. We did invocations already, and you know, it worked okay on OpenGL 150, even though we didn't do the invocations. I was pretty sure that was OpenGL 4. But it was earlier than that. Okay, in general, we can't run these things in a loop or do like recursive generation or whatnot. So in particular, we have this bushmaker, shrub maker, that operates recursively and makes these trees. And the indentation is still weird. There we go. That's not. So we can't just take our vertex or our algorithm here and put it into the geometry shader and make these things since it's recursive. We could turn it into a non-recursive algorithm. That's allowed. It's probably not a very good idea to do that. One of the reasons is we're using randomness on those trees. To get randomness in your geometry shader is a little bit of a trick, but it can be done. You can just put together any random algorithm you like. But if we have true randomness going on in our geometry shader, then the tree would be different every frame, which would look a little weird and flickery. If we were doing it in a deterministic way, like take your random number generator, seed it with the coordinates of the vertex, for example, then we probably could regenerate the tree every time we went.
Is anything actually truly random?
On a computer, not really, but if we manage to seed it, like say we take the elapsed time and put it in as a uniform, so that's available in a geometry shader, and then use it as a seed.
Yeah, that's just easier though. If I was using, I mean, it's all pseudo random still.
It is, yeah, and then the number of times between frames is kind of consistent anyway.
Yeah.
So I imagine that if we had that in our game, eventually somebody would come up with some way to predict when the foliage was like short for one frame, and they'd find the perfect sniper nest that you can only see occasionally.
Yeah.
We're crypto random.
Crypto random. Oh, inside there?
Yeah, instead of just random, it's crypto random.
You have to, a lot of the libraries don't actually work inside there. Like, I don't think I can just say random inside the shader.
Oh,
Actually, I think rand is one of the things that are funny enough.
Can you?
Yeah, it'll give you a float between 0 and 1, I think.
Oh, really? Rand?
I believe.
That?
I hope I'm not messing with words.
See what happens. Undefined variable rand. What's a parameter
Let
type?
me Google it, 'cause I could have sworn I did that once.
Really?
What just ran on?
I don't know, it might not be all.
When I threw it into Google, I got instructions on how to implement a simple random number algorithm inside the vertex shader.
I could have sworn I did it.
You might have to pass it in as a uniform or something.
That's Unity.
Yeah. Oh, well, if you find one, that'd be cool.
But you could implement a small random number generator that uses a seed and then pass in crypto random for a seed.
Yeah, you can do that. Yeah. And if they have the, if you use a consistency, then the trees won't actually draw differently every single time. Which would be great.
Whoa.
Yeah, we lawnmower the half of it.
Yeah,
When
just
it's
half
at
of
a
it.
certain point.
It's a sideways lawnmower.
Oh,
That's a really weird sideways lawnmower, you know?
Yeah. Yeah, there's actually, I feel like this can't have been in the Darwin Awards because it doesn't seem like a severe enough injury. But I read a funny story about somebody that actually used their lawnmower like that to lawnmower a hedge. And they slipped a little bit and lost some fingers, and they were at the hospital being reattached. About an hour later, somebody came into the hospital and they were using their lawnmower to trim the hedge. And then they'd accidentally gotten their fingers in it and needed them reattached. And so the second person said, well, I saw my neighbor doing it. It looked like a good idea.
That is a good idea.
I don't know if it was true or not. It was some internet mail forward from 20 years ago.
I remember the Darwin Awards going around those sorts.
Usually die for technical.
Do you find it?
They usually fall.
no, I
they usually
must
fall
have
in
like
those
found the
kind of things.
implementation for that wasn't built in.
Oh, okay,
So,
yeah.
Sorry.
Yeah, so that's the kind of thing I was finding.
Yeah, like you can get lots of do-it-yourself.
Right. And that would actually work just fine. You probably don't need true cryptography grade randomness inside your geometry shader.
Yes, we do.
Sounds like something we need.
You might better think about the compute shader. Okay, so so parallel, yes, okay. Now, doing one of these things, since you can't have recursion, you have to do everything as a loop. Now, if you did want to do something like some kind of landscape generation algorithm that runs like 5 recursive steps, you could probably get it to work using feedback, which we haven't got to yet, but we will soon, hopefully. Or you can write stuff into a buffer inside a geometry or vertex shader, and then you can actually read from that later again. And so one of the demos I was looking at on it was too complicated. It was like 1,200 lines, but basically they're using it for particle simulation by having the components of the particle written back into the buffer again. So I'll get a simple version of it at some point and bring it up here. Okay, so you can do that kind of thing. Yeah, okay, uniform variables. You can access uniform variables inside the geometry shader. So if we wanted to in here, since we have our MVP, we should be able to talk about MVP. If we declare the uniform up here. Uniform map for MVP. Okay. So this is going to throw everything out of whack. We're applying our transformation matrix twice on some points. And on the other points. But since we have MVP available here, we could say on times MVP, and then these ones say times MVP, and in this one say times MVP.
I just feel like that's going to cause us so many.
Well, it will in the short term. If we run it like that, then yeah, we're applying our matrix twice. And one of the things our matrix does is zoom out. And so we've actually zoomed out twice, and we've rotated twice, and we're into culling in a really weird way now because it's done in an intermediate once applied space instead of the one we're viewing it from. So it all gets a little bit weird. But then we can go ahead and say, look in our vertex shader here, and basically take out this MVP reference right there. That's going to change the way the colors happen a little bit.
Oh my.
But let's take off the culling. And so that was in the, there, this is the culling up here. Okay. Okay.
Uh-huh.
Something's a little weird there.
They're dancing.
Look where all the rotated.
Look at that all disabled. Yeah, it's not used at all in there. We're using it here, here. We take the position, multiply it by, oh. I wonder if that's going to actually cause a problem. Let's see if we get one that's right now. Yeah, we got one that's right. Let's see the other one too. Oops. Well, yeah, it does in the, I don't know how to G it. Okay. Yeah, order matters in matrix multiplication. And I sort of had forgot that. Okay. So if we take that out, then everything should be good. There we go. So now everything looks right again. So if we put our culling back into here. So, oh, the wind is still applied in the vertex shader. That's why they are going into and out of the disappearance lawnmower using the wind. But you can see now our culling plane is actually rotating with the tree instead of with the screen. So basically, we changed our geometry we applied our matrix here in a geometry shader as opposed to the vertex shader. So the vertex shader really doesn't do as much anymore. And actually, we could probably do the same thing with the wind. We got all this wind stuff and whatnot. Let's do this. Got cube.v.glsl into cube.d.glsl. And I'll take the G version down here. We'll still steal the wind from the vertex shader, take the wind out of it. And then the wind is happening right there. We're taking the X display coordinate and varying it based on the wind. So I want to do something very much like that. And that can happen up in these things. We're getting to the point here where we're doing a bad job on code redundancy. Okay, so we took the X displacement and calculated it like that. This is not, you know, chord 3D.x. This would be GL at position 0 dot GL position. And same modification here. Okay. So then all of that stuff is good except for this. Okay. So that should be applying the wind, except for
You still
this
have
bit
another
down
chord.
here.
You still have a chord 3D in the
Where? Oh, right there. Yeah, you're right. Okay. Okay. And yes, that one. So that's an awful lot of like typing and changing stuff here. Okay. So that's applied to one of them. Of course, the actual vertex shader applied that to both of them. We have to do that for both paths here. So at this point, we need to refactor our code here to avoid some redundancy, because otherwise we're going to be typing the exact same thing like 4 times. Should be ridiculous. But you see how we could actually take the functions from the vertex shader and move them all into the geometry shader. So then our vertex shader does next to nothing. And that's certainly possible. You can kind of eliminate your vertex shader if you want to with the geometry shader. So yes, we can just kind of not use the vertex shader. Now we have to give it a vertex shader anyway. The vertex shader is mandatory, so is a private shader. So you can't just load up your program and say, we're going to do away with the vertex shader completely. And as long as you have it, you might as well use it. For example, this geometry shader is run once per primitive. Vertex shader runs once per vertex, so it normally runs more. So you get better parallelism by using the vertex shader to apply whatever you can apply inside the vertex shader. But you certainly can. Okay. And so yes, we can do that. Okay, let's talk about normal vectors real quick. Hopefully, well, won't be that quick. Okay, so hopefully all that stuff there makes sense. I need to copy this to my software. I'll type with the date, September 10th. Okay, so next thing. Turn that over? No, I didn't. Okay. I'm really not using Git in a very Git-like manner by SCPing Git repositories around it. But the funny thing about Git repositories is they really don't mind too much when you do stuff like that. Okay. So let's, I got here, yes I do. Okay, so. Oh. Here is the cube demo, modified in yet another way, yet again. Well, it is. There's a cube, but the corners and the faces are marked. Okay, so let's talk real quick about normal vectors. Well, not necessarily real quick. I always say real quick, like things are going to be faster if I say real quick. Everything will be better then, you know. Let's just go to the store real quick. That way it only takes half an hour instead of an hour for some reason. Okay. It really has a radar detector, so you can actually go to the store real quick. This is a clocks all the time from door openers at gas stations and things. Didn't realize they did that. Okay, so suppose you have a I'm having trouble drawing 3D again. Okay, suppose you have a thing that's actually three-dimensional, like this eraser. And I suppose it's just like it's not a cube, it's like a rectangular prism. But suppose it's just made up of a few triangles. I realize you have to use a lot to get the level of detail of this thing, especially the fuzzy edge here. You could probably have your geometry shader generate you something for that. Okay, so if you take the faces on here, the usual normal vector for a face points straight out of the face. So you can make a normal vector for any of these faces here. You can also have a normal vector on a per vertex basis, because you got vertices at the corners, and so you can have a direction that they are facing. It's used for lighting calculations and things like that, but it can also be used if you wanted to, for example, have the eraser explode and have the pieces move out, keeping their consistent orientation at first, or something else like that. Basically, it just gives you an indication of what direction your surface is facing and what is perpendicular to it. So that's a per face normal. And so what I've drawn on here is not quite the per face ones. It's sort of drawing it like there's a per vertex one, except that the vertex ones actually aren't specified in here. There's a OpenGL called GL normal, and it was used for a long time to specify normal vectors. So you can just say, okay, this is where this thing lines up. But nothing like that has been called in the cube demo, and so I don't think the cube demo actually has normals at all in any way, shape, or form. So let's take a look at the geometry shader right here, the normal vector showing one, except that that isn't actually what that one does at all. So let's look at the normal vector showing one. Okay, so if you have a triangle, you can figure out a normal vector by using just a little bit of math, and that'll tell you which way it's facing. Now, you can have a triangle that's facing backwards by doing this, and so you can actually set the sides different colors or something if you wanted to. You can tell on this. But anyway, so we got a triangle with 3 different places, and it doesn't really matter which one's which for this. Let's call them A, B, and C. Why not? Okay, so A and B up there, we just take the coordinates of 2 of the corners and subtract them and get the differences between A and B and their C. And so this gives us the vector from one of these points to C on each of these. And then the normal vector is actually just the cross product of those 2. And so remember, when you have 2 vectors and you take the cross product, here, pens are good. Okay, so we got 2 vectors here, and we're going to take the cross product and get something that comes out perpendicular to both vectors. So once you've got something that's, oh yeah, sorry about that. So once you've got something that's perpendicular to both vectors like that, that can define the normal vector for your face. Because, I need more pens. I'm glad I restocked the pens. That was an opportune time. Okay, I like an equilateral triangle here. Okay, so suppose you got a triangle like this, and so there's your triangle, and then you calculate something that's perpendicular to both of the vertices. Now you've got something that sticks straight out, looking away from the whole mess. So that'll be a per face normal value. Now the vertices themselves could be potentially pointed a little bit different. For example, if this triangle represents part of a contour or landscape or something like that, you might want to have the normals a little bit different on the vertices from the way they are for the face as a whole. But anyway, that's what we're looking at. So I can set the whole thing up like this, and then nobody can see it. Although we could borrow Alex, and he could see it. Nobody else could, and then he'd stay wherever he's at forever, because he'd be able to see better. Okay. Anyway, so I think you guys can tell what I set up there, because I was talking about the normal vector heading out, so they're all flat there, and then you got one heading out. Okay, so the cross product gives you that. And then we got the whole normalize thing. Okay. So if you, I should say normalize vector, that's probably better. Okay, so it's just taking the length. So if the standard vector is length 1, you have to normalize a vector, you take it, and keeping it pointing in the same direction, you make its length 1. And then you have a unit vector. So that's what we've done. So if we take out that normalized function right here, then the vectors ought to be a different length. So Sure, why not? Yeah, now they're longer. Cool. You need to play with the clipping plane there so they stay visible. But anyway, so there's that. Okay, I'll put my lines back on. So we get the cross product to get something that's perpendicular to two of the vectors, and that gives us a normal vector. And so the average there, I'm finding one for the center of the triangle. And so each of these has one drawn at the center. We could draw the center one a particular color or something, and that would make it obvious. If we say like F color, it's using FCA, it's vec. This takes a vec 4, 0, 0, 0. That should show up well against our black background or white background. Or not. Oh, I think I made it fully transparent on accident. There we go. Okay, so the center ones now are done that way. You can see how they're kind of set there. So our cube, remember our cube is made up of 12 triangles, not 6. The cube has 6 faces that are square, but if you want to draw these things in triangles, then each face is going to have 4 corners, and in order to make this a triangle, there is a line right across the center. And so you have actually 2 primitives, each of which is a triangle. So if we're finding the center of these, we'll actually find this spot and this spot as the center of a primitive. And so once we got those 2, then that's going to make it so that we see, hold this thing up again here, these kind of 2 offset little normal vectors right there. We're not actually drawing a cube behind them, so nothing to see there. Okay, so that's what the averaging thing is about. So we just go ahead and average each of the 3 corners, and that gives us the center. Where's the division? I don't even know. Maybe I didn't do it. Okay, so anyway, we're figuring out the average of the 3, possibly without actually dividing by 3 at the end. And so then that's one of those ones. Okay. The other things, we got 3 corners there, and so in this case I used a loop because I was getting tired of cutting and pasting and making manually unrolled loops. And so we can do loops, so let's do loops. Okay, so for each of these normal vectors, we take the original vector position and draw it, or the original vertex position, and that is one end of our line. And then the other end of our line, we just take the other end of the vector, and out it goes. So that way everything's slid over by 1 normal. Okay, so that ends the primitive and whatnot. Okay, so that's kind of the original normal one here. So let's do this. I'm going to make this normal back GL.SL, and that way everything will be on the examples. Okay, so suppose we want to spit out from this cube demo a cube, but then we'll take each face and scoot it out and have an extra face. So it's like a cube, but then it's like, yeah, duplicated further. Okay, we can totally do that. So first of all, we're going to want to put out triangles. And unfortunately, we're going to have to say triangle strip. I guess it's not super unfortunate. There's nothing that's really hurt. But you know, it's the way of things. Okay, so now, for each of these, we're going to have a triangle, and then we're going to have a triangle 1 further out. So if we just want to draw the original, we'll leave our normal vector calculations in here. We don't necessarily need the average thing, which was probably all messed up anyway. We just need this. So for the original, we want to take each of the vertices and re-emit them the way they were before. And so we just need to emit the vertex once each time in this loop. So out it comes, and we're averaged up. Okay, so I think this should be a entirely benign geometry shader. See what happens. Notice I haven't actually recompiled the demo yet. Oh, unknown layout specifier. I think it's maybe triangle strip. Okay, we said 8 for max vertices. Oh, that's not good. Oh, we end primitive like 3 times, once per vertex. If we end primitive on every single vertex, then we're gonna have a problem, because each of the triangles only have 1 vertex.
And
Right.
Doesn't sound like a
Okay.
huge problem.
So there's our original triangle. Cool.
That's
I think the vertex shader or something, I have zoomed out in some way. Okay, so that's the original one. So, for this other one, what we want to basically do is take this and add on the normal for each of these positions. Let's see what happens. Oh, well, normal's on the vector. Okay, so now you can see the cube has been lightly exploded by taking these things out. So, having the original cube on the inside basically means we can do it this way and then do it the other. We already have 3 invocations drawing the exact same thing on top of each other, which we shouldn't have. So let's drop that down to 2, which is more the correct normal, and normal. And we'll just put in 2 possibilities in here for this line. Okay, number 1 way is if, I need to think for that. And int deal invocation ID. Okay,
semicolon,
good point. I forgot that last one too.
that's why I know.
Okay, so that's true, we'll do it that way. Else, we'll do it that way. See what happens. There we go. So we got our cube in there, and then it's got like kind of the armored things. Now, you see they kind of pop in and out of existence. I think we got 2 things going on here. I think the clip plane may still be set wrong, and that's a possibility. We can see the backs of them, so it's not the backs. It could be that, or it could be that our sign is reversing on our vector and popping them inside the cube sometimes.
Well, the bottom one's not there.
Yeah, the bottom one doesn't even exist.
So let's see what we can do about that. So we'll go ahead and take this and we'll move it up to 3 invocations. And so that's a possibility there. It could be 1. I think invocation is 0, like 0, 1, 2. So that's another possibility. We need an LCSC. And then final possibility, take this, and we'll take the minus sign in there. Oh.
Put a 1 in there, apparently.
Yeah, 1 is a good minus sign sometimes. Okay, that actually changed the number of invocations.
Yes. Oh, that just made it weird.
It's like an open face cube.
Well, yeah, the drawing order is ending up wrong. Because it's drawing those ones that are inside it in some cases after the others. I thought we had the depth buffer test turned on, but maybe I'm wrong. Maybe it's off. Okay, so that was a lousy idea. I'm not sure why they're popping in and out then. Maybe just a clip plane. That'd be my next guess. Okay. Anyway, we got our slightly armored cube. Let's go ahead and pull them further out and see if that changes anything too. So we've been going with this normal, and we normalized it. And so it should be normalized now, which is cool. And so if we multiply it times like 5, then we've got 5 times the normal vector.
They still blink out of existence.
Yeah, when they get far enough away.
Could you make them larger? That way we'll be able to see them if they pop inside.
And where's the bottom one?
Oh, like make them larger than it is? Yeah, we could. Let's go ahead and take a look at the clip plane
I
thing.
still want to know where the bottom one is.
Blow the clip plane.
Oh, I think there's something else happening here. Watch it spin for a minute. Now, when it disappears, note what had happened to this edge. Suddenly we can't see it, right? If we can't see it, it doesn't need to be drawn. If it doesn't need to be drawn, then its geometry shader doesn't need to run. If its geometry shader doesn't run, we don't draw that extra piece. Okay. So I guess that should be a warning for when you make geometry shaders that draw things that are far removed from the location of the geometry that you're supposedly drawing.
So what you're saying is we shouldn't use them for doing what we're doing here.
No, this really isn't the right way to use them. The lab today has you use them in a much more normal kind of way. Here's a depth test. There, GL depth. Let's take out GL depth real quick.
So that'll cause one set of problems.
Oh yeah. I'm curious if they still disappear. Okay. Well, maybe it doesn't need GL depth to tell it doesn't need to draw it back, or on the other side of the Well, I also didn't. Oh, I didn't change the depth thing anywhere else. I think there's a couple places you have to say stuff about depth. I thought that would turn it on nicely. We're still GL enabling GL depth test right here. If you don't do that.
So enabling.
Okay.
Now you can't tell the depth.
Yeah, we got the depth test going. It's still disappearing. The GL blend function set here, that should be fine. Yeah, I have to think about why they're disappearing. Okay, because yeah, even with the depth test, you think that would still be drawn with the depth test. And they're totally dropping off. Plus they're going far enough now that if they were going negative, we'd see them appear on the other side. I'm just curious now. Oh, that was the other one. Okay. Suppose we multiply this by -5.
With no depth, it looks.
Ooh, those are doing some fun things.
Yeah, let's turn the depth test back on. Oh yeah, so for everybody that wasn't in game design, now you know what the depth test is for. I was thinking we should talk about that one of these days.
So they get closer to it and then.
Poof.
Maybe I'm misinterpreting the clip plane thing somehow.
Maybe there's another thing other than the depth test, that's the background text.
Oh yeah, like is it on the back side of the exact thing it's from? Yeah, it could be. Okay, well anyway, I guess we'll just leave that as a mystery of the day. Okay.
Or maybe the primitive cube is set up so you can only ever see three sides of it at once.
Well, it's not a primitive, it's a cube. No. Okay, now I'm gonna be thinking about that like ever. Okay, so we made neural vectors, talked about neural vectors. Cool. Oh yeah, that was a note. Oh sure, why not? Okay, so there's with this tree and the way the tree does everything, it ought to be using vertex indices, but it's actually not. If you look at the cube and the way it's drawn in this cube demo, we have the cube vertices here, and there's 8 of them, and we have cube colors, but then later we have cube elements. And the elements here tell us which indices go where in order to draw the triangles. And so this is actually references to the vertices up there in the vertex list. So we're able to draw the complete cube, 12 triangles. 12 triangles would be 36 corners of a triangle, but we're only actually using 8 vertices. And so that gives us pretty good efficiency. Each corner of the cube is actually the corner of 6 triangles because you got 2 triangles in face, have a corner there, and you got 3 faces that are against each corner of the cube. So our tree really ought to do something real similar to that, and that would make the tree 1/3 as big. But then we'd have the element array, which would add back on some of the space savings. But overall, we still save quite a lot of space to set things up that way. It's simpler just to do it the way it is, but it's not better. I used to have this file format. I probably still got a bunch of stuff around it, SLO format. And a friend of mine named the SLO format. I'd just been making it and putting it in these files and just putting .txt at the end or something. But basically, it was a list of vertices, exactly the way our tree works right now. And they were put out in ASCII text, like numbers in ASCII text. So a friend of mine named it an SLO file, which he said stood but she said stood for Seth Long object. But I knew that it was actually a commentary on my file format and its efficiency. Since it stored a lot of the vertices 3 times, and with them in ASCII text, of course, it used way more space than a binary format would have.
So, how's that a commentary?
It's slow.
Yeah.
Oh,
Okay, so lab today. I'll put a basically copy and paste this into the lab description and post it as lab 3. You get to draw the cube with bulging sides. And so use the normal vector stuff. And basically you just have to take the hypotenuse, find the center of it, pull that out. And then instead of one triangle, you'll draw 2 triangles. So you clip that right there and pull it out. And so then the end of it is 4 triangles total. So for every 1 triangle, you run 2. And then it'll have little bulges. So geometry amplification. It's an original use of geometry shaders, and a lot of times it's done the tessellation shader nowadays, since OpenGL version 4. But it really shows you what the geometry shaders are supposed to do, as opposed to being kind of silly with them like we have for the past hour.
Yeah, but being silly with that is more fun.
Well, sometimes being silly shows you kind of what they do, you know? Like, oh, it does that. You can make a copy of something with one. Kind of like, you know, the first thing you do with a copier is you're like, well, what is the range? Does the paper have to be there? Can it be taped to the ceiling? It's a zoom. You don't really learn what a machine is until you figure out what it can and can't do.
You figure out what it can and can't do, and then you make it do things beyond its specifications.
And you learn a lot about it. And then you know a lot more about it in regular use. And then you can be the life of the party too. Because when you're standing next to the copier, you know, you can tell your colleagues, do you know you can actually put your paper as high as 8 millimeters above the display and it'll still image it with good clarity?
The worst part about that sentence is it totally sounds like something he's done.
Actually, I never have. No, I just thought of it while I was sitting here playing with this street sweeper bristle. I think that's what this is anyway.
I can tell you.
I'm betting that it's Jesse's.
is it slightly bent?
Yeah.
Yes, it's a street sweeper.
Yeah, I think I found it on the floor the other day instead of there. I had to tell him about it. Okay, well, I'll see you all next time. Have fun, Alex. Everybody else will see you this afternoon.